Hey everyone. In this video, we're going to be looking at a fact in math that's often taken for granted, which is that the definite integral of a function actually represents the area under that function's curve. Or a bit more precisely, the area between the function and the x-axis, the signed area, that is. Almost everyone who's learnt integration knows this to be true, but the reason why isn't really focused on, or even some basic intuition as to why this is the case. Most people don't know. Because it is a bit of a magical thing that all you need to do is calculate the antiderivative of a function, and by just substituting two endpoints, this number you work out will be exactly equal to this area. So the purpose of this video is to give a semi-rigorous proof as to why this is the case, but focus on the intuition as to why it's the case. So let's imagine you just had an ordinary function and two endpoints, and your task was to calculate the area under it. If you were to sort of do this with pen and pencil, you would probably try and split this area underneath into shapes that you can actually calculate the area of. And so in the HSC syllabus, there's this thing called trapezoidal rule, where you split it into a bunch of different trapeziums, right? An even more basic shape is just rectangles. So you can imagine what I might do is I'll take my region that I'm trying to work out the area and split it into different little chunks, that all have the same distance. So maybe we'll call this x2, x3, we'll leave some gap, and this one is xn minus 1. And then we go to b. And what I can do is I can, basically convert this all into different rectangles. Now it doesn't look like it, but imagine all of these have the same distance or the same length, and let's call this distance d. So we know the length of all, or the width of all these rectangles, and the height of them is just determined by the height at this x value. This rectangle, or each of these rectangles have the height based on their left endpoint, right? So I've drawn them across like this. So this rectangle has height, whatever the function's height is at a. So it would be f of a. This rectangle would have height f of x2. This rectangle would have height f of x3, and so on. This last rectangle would have height f of xn minus 1. Cool. And so this looks like a very inaccurate area estimation, but you can imagine as I shrink d and cut up into more and more slices of rectangles, this will become a really, really accurate representation of this area. In fact, if I send d to 0, if I consider the limit as d goes to 0, this will actually approach the real area. And so what I can say is the area approximately equals the area of these rectangles. The first rectangle has height f of a and length d. Second one, f of x2 times d. And we go all the way to the last rectangle, which has height xn minus 1 and again length d. So the area is approximately equal to this, and we might say that it is completely equal as the limit goes to 0, right, of that same thing. So I'm abusing notation a bit. When d goes to 0, that's going to change the number of these points. So these aren't really the same, but yeah, hopefully you get the intuition. And the area is exactly what the definite integral is, right? This quantity that we're calculating is supposed to give us the area. Now, each of these values, remember another piece of notation, we use capital F for the antiderivative. So what this tells us is that the derivative of your antiderivative is just equal to your original function f of x, right? When we integrate, we find the antiderivative, and so capital F's derivative is just whatever's the thing you're integrating. And so what I can do is I can replace each of these f of a, f of x2, f of xn minus 1. I can replace all of them with the derivative of the antiderivative, or the derivative of the primitive. I hope that's pretty believable. Yeah, this is just notation for the primitive of this function, and so we can replace this as the derivative of this. Why do we do this? Because as a quick aside, hopefully you remember from, maybe I'll need a bit more space than that, hopefully you remember from differentiation, first principles tells us that the definition of the derivative of a function is you can sort of do the limit as h goes to 0 of f x plus h minus f of x over h. Now obviously the h it's irrelevant what letter we use here, right? Whoops, here, here, and here. We could have as easily used d. Maybe I'll just do it like this. D goes to 0 over d. And so what we can do is, if we for a second just ignore this limit, and this is again abusing notation a bit, if we treat this as a fraction, we can form an identity by bringing d to the other side. F dash of x d equals to f x plus d minus f of x. And this is true at the limit. What this is saying is the gradient tells you the rise over run, right? And so if you do your gradient times by how much you're running, that will tell you basically the difference in height. Yep. So this statement is true when d is very, very small. The derivative times d will equal this difference. Now, in our case, this is true for all x values, right? For all x values of this function. And so it's true even if we substitute specific x values. Now, why we want to do this is, notice this is extremely similar to what we have in each of these terms. So if I substituted f dash of x2, for example, or maybe we'll start with a, that would equal f x plus, a plus d minus f of a. But what is a plus d? Well, a plus this distance will just take me to the next x value, x2. And this will be true for all of them. If I want to find out x2, this is just going to be x2 plus d, or x3 minus f of x2. And you can sort of see the pattern. And so we can use these substitutions here and chuck them into our integral thing that we're working on here. So if I sort of resume from here, what I have is, because both of these things are true at the limit, this is equal to f dash, instead of f dash of a, we're going to substitute that for this. We're going to substitute that for f of x2 minus f of a. And then the next one is, as we have here, f dash of x3, no f dash. F of x3 minus f of x2. And we keep going until the last term. So what's the last term? Well, we have f dash xn minus 1 times d. So what would that one be? The first term is the x value after that. So it's this plus d, and the value after xn minus 1 is just b. So we have the last one is f of b minus f of xn minus 1. Sorry, that's a bit squished. Cool. Now, this sequence, when you're summing a bunch of differences, is a very common pattern in math, and it has a fun name called the telescope sequence. Because when you do this, basically all the internal terms, the middle terms cancel out. Notice we have here f of x2, and then we're minusing f of x2 here. And similarly, we'll have f of x3 here. I haven't written it, but the next term would be f of x3 minus, sorry, f of x4 minus f of x3. And so the x3s would cancel. And so all of these terms end up cancelling. This f of x minus n minus 1 term will cancel, and you're just left with the starting term and the ending term. And that's why it's sort of like a telescope, right? This is a horrible telescope, but a telescope expands like this, and then it can just completely, when you collapse it in, it just collapses, so you just have the first and last term. And so this whole expression collapses to just this last term, f of b, minus this term, f of a. And that's exactly what we calculate when we want to find the definite integral. So hopefully that gives you a bit of intuition as to why. All we're doing is we're estimating the area with these rectangles, and it turns out, because of first principles differentiation, right, each of these areas is nothing but the difference of the antiderivative. That's where it comes in. The difference in heights gives you an estimate of the area of each of these rectangles. And if you sum them all up, all you're left with is the first and last term. And so when we do differentiation or integration to find such a complex thing like area, all we have to do is find the antiderivative and sub in the upper and lower bounds. Cool. I hope that makes sense. Let me know if you have any questions.